Okay, now that you've taken the quiz for the first part of this, the material that we've covered so far really is only about the first 3 or 4 slides on this. We're going to go through the next few slides very quickly because some of it actually applies to real life, some of it applies only to the test. I need to go through all the material so you can pass the certification test. However, I'll also point out what applies to real life and what doesn't. So, this first slide, we've gone over this 100 times. And again, I highly recommend you have a separate page in your notes for Lesson 7 lectures so that you can access that also. And then if you're not familiar with the search function in Microsoft OneNote, you need to get familiar with it. I'm more than happy to show you, again, how to use it. Okay, so WAN technology, wide area networks, connect multiple local area networks, that's easy. Local area network, does a local area network have a router or not? Jill? No.
No.
Yeah, your answer is no.
Me.
Okay, local area network does not have a router, right? Wide area network, by definition, does have a router. That router can be an appliance, like a Cisco router, or it can be what else, Taylor? An RAS server. An RAS can be from your actual machine. What else, Josh? A layer 3 switch is also a router. Layer 3 is what layer? Austin?
It's the
Wrong. Thank you for playing. Next. Larry.
It's the network layer.
Network layer. Okay? Network layer. You knew that. Part of this class is getting used to the pressure, right? Being put on the spot. All right. An organization wishes to have a wide area network, it needs to decide on networking service, the speed at which it wishes to connect. Blah, blah, blah. Okay. If I want to have a wide area network, and the wide area network is in my business, okay? It's in my company, and it's just connecting buildings. Forget the internet. I'm just connecting different buildings. Chances are I want what kind of speed on my wide area network? Jason? Huh? Gigabit, because my desktops most likely are connecting via gigabit. Why don't I want gigabit access to the internet, Aaron? I mean, I do, but why would I probably not design that? Too expensive. I mean, nobody offers gigabit connections to the internet for less than, say, $1,000 a month. And for most small businesses, that doesn't make any sense. It doesn't buy you anything. Okay? However, in your local area network, gigabit technology is not too expensive. You can have that. But if it's between buildings, it's long distances, chances are you're going to have a router in there, which makes it a wide area network. Okay, you also have, yes sir?
I was looking at a company's, their service system and stuff, and they were running a 10 gigabit connection throughout it was like a 100 terabyte system, and they were like a multimedia, like HD 4K kind of stuff.
Yeah.
So I was amazed at the, at how powerful that 10 gig.
How fast that 10 gig connection is. A lot of companies these days, they'll buy routers or switches that have 10 gig uplink ports. What does that mean? Austin, never. Come on, stay with me, pay attention. Johnny, it is the speed of it, but what's of the uplink port? Come on, what's the uplink port on a switch? We've talked about this before. This is chapter 1. What's an uplink port? Yes, Q.
It's like the speed that's going into it. It's like switched with the speed that it's transmitting out.
Okay, so an uplink port is if you're connecting multiple, you're right, kinda. The uplink port is what the port that you use to connect one switch to another switch, or one switch to a router, or if you have 3 switches linked together, you can have a 10 gigabit uplink port connecting those, assuming that your media supports that. Give me an example of some media, Jessica. What's that? No, not that type of media. The media that's connecting switches, yes. Fiber optic, assuming that your fiber optic cable supports 10 gig, which it would if you have the right optics, supports 10 gig, then you would have an uplink port that's a 10 gig on this end, an uplink port that's 10 gig on this end. If I connect two switches to each other, there's another name for that connection between the two switches. What's that called? Most of you don't have this. Yes? Nope. It does bridging, but that's not the physical connection. What's the link between switches? Uplink port connects two switches, and when you connect two switches, especially over long distance, that's called a what? Yes, Austin?
WAN.
It becomes a WAN when you're using layer 3, but two switches did not necessarily mean you got a WAN. Backbone. Backbone. A backbone is the connection between multiple switches. When would I use a fiber optic backbone, Jordan? You have no clue? Yes, you do. Think about it. When would you use a fiber optic backbone? What do you know about, this is chapter 3. Austin.
Like say you have some kind of business that needs
Go ahead.
that needs more space for computers on it than one router can provide.
Nope. What are the most likely scenarios where you would use fiber? Jessica, give me one. I can't hear. When there's large amounts of interference. What's that interference called? Keaton. EMI, electronic magnetic interference. Electromagnetic interference. What's the other one? Q. RFI, what's that stand for? Cheap. Radio frequency interference. Those are the two ways of, those are two types of interference that Jessica mentioned that would necessitate fiber instead of copper, because copper is susceptible to those things. What is another reason you need fiber as opposed to a copper backbone? Give me another reason. Yes?
We're going long distances.
Long distances, because the limitation of copper backbones is what? In a Cat 5e scenario, how far can you go with copper? Larry?
Isn't it 50 feet?
Nope. Cole?
100 meters.
100 meters, which is roughly 330 feet. Okay? You're close. All right. Packet switching. Here's where we get into the echelons above reality. This is what's going on at the phone company. Okay? All right, so let's break this down. This can start to get confusing, but it doesn't need to. I'll say it one more time. This starts to get confusing, but it doesn't need to be confusing. If you think about what they're saying. When I take a 100 megabyte file and transmit it across the network, what happens to that file when it gets transferred across a network? Johnny? It's broken up into packets at the source, and then it's reassembled at the what, Jill? Why did I call on you right then? Because I want to make sure that you're not just typing, you're thinking about what we're talking about. That's the most important part. If you have a packet, it starts at a source and it ends up at there's a term. What?
EMP?
No. It ends up at, what's the computer at the other end called? There's a name that we use all the time. Source and, Jason? Destination. Source, sound familiar? Source and destination. So it's broken up and formed into packets at the source and then reassembled at the destination. Now, if the source is your computer here and the destination is my computer there, how many devices possibly are between that computer and that computer? Austin?
There's that router, and then it would go down router, so wireless access point. It would go out to this
I need a number, Austin.
4 or 5.
There could be 2 or 3 within this network, if it's done efficiently, 2 or 3 different devices. Now within those devices, what we learned the other day is that those devices, if they're routed, if those packets are routed, so in other words, if that's not on the same IP network that that is on, now it probably is, but let's pretend it's not. If it's not on the same IP network as that one, then that means it's getting routed. And if it's getting routed, there may be multiple paths for that. Why would there be multiple paths, Josh? What are the reasons to provide multiple paths to the same destination? It could be more efficient. Give me another one, Johnny. You're on a roll, buddy.
If one goes down, then it'll.
Redundancy. If one goes down, the other one can pick it up. And chances are, if you're doing a good network and you can afford it, then you'll have multiple paths to the most common destinations. You'll have multiple paths to those common destinations. Therefore, we do, in phone companies especially, or in ISPs, or in major telephone or major telecommunications companies, they will use a technology called packet switching. Okay? Now think about what happens. We have packets. It's a very basic concept. We have packets that on that packet is made up of what? What's that packet made up of? Give me one component of a data packet. What's that called? Very simple. Yes, Aaron. Forget the frames. Frames are the first part, then it's joined and joined into a packet. That's not wrong, but it's not what I want. I have the data, right? In a data packet, I have the data, and then what's on top of that data? It's actually called a header. I'm just going to call it that. What makes up the header? At the very minimum, what makes up the header? Destination address, which is an IP address. And what else? Yes?
Where it's coming from?
Source address, so they can get back, so the message can be sent back. And so in packet switching technology, like on the internet, I've got 50 packets, and all they're saying is those 50 packets, based upon routing protocols and routing preferences, of those 50 packets, there's a very good possibility that they are not all going to follow the same path, right? The technology up at GTE, up at CenturyLink, up at Comcast, the technology that's there is going to take all those 50 packets and send them different directions and get them to the same destination. That's packet switching. And how fast that takes place determines how effective that packet switching technology is used. Okay, so within the general category of packet switching technology, we have frame relay, we have ATM, we have X.25. Okay, those are some of the terms that are available to you. Okay, so we have packet switching technologies that are out there. That's the basis of our internet infrastructure. We have packet switching technologies. There are lots of different types, but that's the general concept, and that's the part you have to understand conceptually. We have packet switching technologies and services that make up the bulk of the infrastructure of the internet. That's why, again, if I take a 100 megabyte file and send it across, even a VPN connection, and send it across to a remote location someplace on the internet, the cloud, if you will, your OneNote notes. I take that 100 megabyte file, of the 100, let's say there are 1,000 packets, probably more, 10,000 packets, maybe 2,000 go one path, another 1,000 go another path. There could be 50 different paths that these go, depending on how efficient it is. Someone asked on their exit surveys, which only 14 people filled out exit surveys, out of a class here of 34 now, and an overall class of 50. That's great. Only 14 people filled out exit surveys. Okay? One of the questions on those exit surveys was, what is the difference between IGRP and like OSPF? Or RIP, no, I'm sorry. OSPF and RIP, or IGRP and RIP. Interior Gateway Protocol in general, IGRP is one version of that. EIGRP is another version of that, and then you've got RIP. RIP, very simple. Very simple technology, it's been around forever. RIP and RIP version 2. RIP is going to take a look at the number of hops, and if it's got 3 paths, this one has 2 hops, this one has 5 hops, this one has 8 hops. it's always going to use the 2 hops over here with RIP or RIP version 2. EIGRP, or Interior Gateway Routing Protocol, which we talked about, which can be used in this kind of scenario. It's the routing protocol behind frame or packet switching. If it has 3 different paths, one of the paths that has 2 hops is only a 1 meg connection. The second path in general is a 100 meg connection. And the third path, even though it may have more hops, is gigabit technology. Chances are that its first option is going to go with this third hop. So it's a combination of number of hops, speed of the connections, and reliability of those connections. That's what makes up EIGRP, which is the primary protocol being used. IGRP is what you see in your books. EIGRP is just a more enhanced version of it. In fact, I think E is enhanced. That's the difference between IGRP and RIP or RIP version 2. Now in a small network, when you only have 1 or 2 paths, who cares? You're limited by your connections, not necessarily all these different paths. But out on the internet, chances are you want a sophisticated routing protocol like that. What? Well, it's a combination. I mean, EIGRP and IGRP take into consideration. The question is, what is IGRP made up of? Again, if you look at that protocol, the decision on which path to take of the 50 that are available to it are a combination of the number of hops, in other words, the number of routers in between, the speed, overall speed of those connections, and the efficiency or reliability. So if I have, let's say I have 100 megabit connections all the way through in my second option, but the latency on the connection is 300 milliseconds versus a 10 meg connection over here that has the exact same number of hops. Even though it's a slower connection, if I'm getting 1 millisecond latency, chances are IGRP is going to choose this path over here. Okay, so it's going to choose your best path based upon a combination of all of those factors. Now think about the factors. Think deeply. Don't just look at me and, okay, think deeply about these factors. What is going to make the decision? The decision is speed of those connections, latency, which is the, remember the 600 millisecond, the 1 millisecond, those kinds of things, how fast it gets back. Latency, speed, latency, number of hops, number of routers in between. The more routers, chances are, the slower it's going to be, or the farther distance it has to go. Therefore, the slower it's going to be. And the reliability. You know, how reliable is it? Does it have a history of always being up? Think about that. Okay? But that's done automatically. And it changes. That's part of the dynamic routing protocols. It changes periodically. Not only changes as the path, but it changes as far as the evaluation of those paths. And that's why when you have a Cisco router versus a RAS server may use OSPF. It's certainly not going to use IGRP or EIGRP. That's what the difference is between a $5,000 Cisco router and a $150 Linksys router. Okay? As an example. So, packet switching. X.25, nobody uses this anymore. First implementation of packet switching, it says it's still in use today. It might be still in use today in analog phone connections, which almost no one has anymore. Okay? Packet switching, actually I just lied to you. It would never be used in analog phone connections. It might be used in the original digital kinds of phone connections. It's originally created to break down large messages into smaller, more manageable segments for transmission over a WAN. Why do we need manageable, why do we have to break packets down at all? Yes?
Well, sometimes, like, the places being sent to can, I guess, I'm thinking the word, I guess, read it, or cipher it.
Someone give me another answer. Yes?
If someone were to like hack into whatever you're sending, they can't see the full file, they can't see the tiny packets of paper.
So you're saying a denial of service attack?
Possibly.
I've heard by some really large files that are bogged down.
Why? Why would it bog down? Why can't they just all send them simultaneously? there's a technology that we talk about that limits, for obvious reasons, as soon as you define the term, that limits us as far as how many packets we can send at a time. What is that technology? In an Ethernet world, what's that technology called? Yes? When you're talking on a network, when I have, let's use electronic media. Let's use Cat5 cable. Now, at the phone company, you're not going to find much Cat5 cable. You find some. If I have a cable going from here to here, and it goes to a switch, okay? That cable can handle, at any one time, that's an electrical circuit, right? The circuit has to be maintained. If I have a circuit from this computer to this computer, also from this computer to that computer, but that same circuit here is transmitting from Zach to that computer, it can maintain the circuit from here, but it can't maintain both circuits at the same time. So while he's transmitting, he can't. After he gets done transmitting, he can. Now think about what I just asked you. Why do we break down larger packets? Why can't we send 100 meg at a time? Because the circuit, you don't want the circuit being up for the 5 minutes that it takes the 100 meg connection or 100 meg packet to cross that circuit. Because you want other people to be able to talk also. So it breaks it down into smaller packets. We'll send a few packets, somebody else, and we'll send it, and then the next person will send it, so on and so forth. There is a term that we use for Ethernet. Does anyone remember what that term is? Do you remember what the term is? Answer my question, otherwise don't raise your hand yet. Do you understand? Do you know what the term is? Yes. What's that? No, that's a physical connection. That's a physical connection. There's a term. It's called CSMA-CD. Carrier Sense Multiple Access Collision Detection. That's what says only one device can talk at a time. That's why we went from a hub to switches. Because now instead of having one giant circuit that connects 8 devices or 16 devices or 45 devices, we have 16 circuits or 45 circuits or 8 circuits, depending on how many ports we have. Yes? CSMA, Carrier Sense Multiple Access. And then there are different versions. There's collision detection, collision avoidance. Yes, now what's your question?
Yeah, the answer I gave about like when something wouldn't be able to, if we would need to downsize the packet or change the size of the packet, I was saying that the other destination couldn't read it. I was talking about IPv6 to IPv4.
Okay, don't confuse, yeah, two entirely different things. Now you did bring up a point. In addition to breaking down the packet into manageable pieces, when the router analyzes its different sources to its different destinations, it comes up, and you don't have to know this, just in the back of your head, you might have heard these terms. It also determines how big that packet is. It's not only going to break it down into a predetermined number, it's going to break it down into the size of the packets based upon what the network can support. As an example, if I have fiber going from Johnny's computer to Austin's computer, and I have copper going from Johnny's computer going to Quentin's computer, both of them, the MTU size of the packet going from Johnny's to his, which is the packet size, might be 3,000 versus the MTU going to Quentin, which is kind of a standard MTU, is 1,500. Now, once you get beyond this class and you decide to go and get advanced certifications, get your full TCP/IP certification, you'll learn, and this is what makes you, why Cisco engineers and why people who do what I do make a little more money than just somebody gets basic certification. Because now you buy $5,000 routers, which I've seen this happen. You buy $5,000 routers, which the owners are investing their money in, expecting a $5,000 return, right? And what happens is they're leaving default settings. And they don't recognize that that router and all of the infrastructure around it that you've invested in heavily needs to be able to support those larger packets. And so you tweak that network based upon what it's capable of doing. The other rookie mistake that I see is you'll have a $5,000 router here, and then they'll have connected to that router and connected to the rest of the backbone, they'll have $150 switch. The $150 switch is maybe only capable of handling 1,500 NTU packets, which means much smaller packets, which means many more packets. And the router itself is capable of handling 3,000 NTU packets, but it's being throttled down to be able to support the least common denominator over here, right? You all know what a least common denominator is, right? So why not spend a little bit extra money in the cabling and the switch and everything else and have an entire network? Or better yet, if you don't need that speed, don't buy a $5,000 router, right? Don't spend that kind of money on it if you don't need it. Okay, so that's X.25. Okay, data is gathered. Okay, so this is technology, like I said, that was used in the past. And in some cases, is still used to telephone companies. I have, of all of my internet connections, of all my network, wide area network connections, I can't think of a single instance where we're still using CSU DSUs. You need to know what a CSU DSU is, though. Okay, so in the old days, we had Cisco routers, and the definition of a router says it has to have at least how many interfaces? What? Two, right? Because you're routing between networks. Well, in the old Cisco 1500s, as an example, we had a built-in CSU DSU. Okay? Think of it like a modem, but on a digital level. Okay? We had a CSU DSU plugged into a port on the router, or the pad, when we're talking about X.25. Another name for a router in X.25 world is a pad. Okay? And then it converts it to a digital signal on the Ethernet port, or on the fiber port, or on the whatever port. And so a lot of times what would happen is the phone company would bring in this, this connection for the internet from their equipment. It's a unique connection. And it would come down to their modem, their CSU DSU, and then you would connect to your router and route copper to copper, or route Ethernet to Ethernet, or your router itself would include the CSU DSU, and then it would go to an Ethernet connection. I know that sounds confusing because it's not what you see now, but that's what we used to have. And in some cases, I'm guessing they're still out there. For your test, you'll still have that. In most cases, in the last 15 years, 10 years, the router and the CSU DSU are combined. Okay, that CSU DSU is included in the router, in a port in the router. Okay? Questions? You don't understand it, or it's just whatever, let me know. Picture is worth 1,000 words.
Question.
Yes.
So essentially what it's doing is that it's taking, a block of information that's
In one format,
yeah, and then like cutting it up.
converting it, not necessarily, in some cases it can be combining them, but converting it to a different format at the router.
Okay.
At the router interface, or at the CSU interface. Okay, so pretend that this is analog, one function of this, right? Analog signals. Comes into the CSU DSU, which could be just a port on this guy. Comes into the CSU DSU and it's converted into digital signal.
Okay.
And the digital signal now has an IP address of whatever. And it gets sent over to a different network over here, a different IP address over here.
All right. So would this be like phone connections and stuff?
Correct. Okay. All right, so X.25 cloud. What they're depicting here is that cloud that you see in the middle could either be private, this is important, that X.25 cloud could be either private or it could be public. What do you think I mean by that, Frank? What would be an example of a private X.25 cloud? What would be an example of a public X.25 cloud? Aaron Kleckner,
Be like for a business where they would,
would that be private or public?
private,
Okay, what would be a public example? You're right.
just like a public, like a library.
No. No. No one knows? An example, yes, Jason?
It would be something like a public website uses
Nope. Okay, a private X.25 cloud is one that I'm using. I'm a business, like Aaron said, but I'm using my own technology. I'm my own routers, my own switching equipment, my own X.25 backbones. Wholly owned by me. Doesn't have anything to do with the internet, doesn't have anything to do with the phone company. A public X.25 cloud is one that I contract with AT&T, CenturyLink, whatever. I may own the equipment at those remote locations, New York, wherever the one is in the upper left-hand corner, Los Angeles, and Atlanta. I may own the equipment there, but I'm using the telephone company or the communications company's infrastructure in the middle. So it's not just me sending packets within there, but other companies also. Now, very, very important topic, or very, very important point, and that is, for many, 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 many years, when we first started coming up with these kinds of technologies, and we first started having, from the point that we first started having companies in different locations want to communicate with each other digitally, that section in the middle, not only X.25, but ATM, so on and so forth, was completely and wholly dominated by just a few telephone companies. AT&T, GTE, AT&T got broken up into all the baby bells, right? Literally the baby bells back in the 70s. Okay, and then all these companies started breaking out. There was deregulation, and companies were popping up all over the place to provide these same kinds of services. No one used their own. Okay? Because you don't have the fiber going from New York to Atlanta, which is what it would require. So people would lease from these companies. People would lease space on their cables, on their equipment from AT&T and GTE and all these other companies. Now, in 1994, 95, before most of you were born, all of you were born, 1994, 1995, I ran into the first time that we broke away from this kind of configuration. And a company could actually do it cheaper because by using the internet. Okay? By using the internet. So instead of contracting with AT&T to have their own private, God bless you, their own cloud within, secure cloud within the AT&T public network, instead they were able to use anyone's internet connection and still securely connect all of those cities at the same speed, if not faster. It was the tipping point where those companies started losing ground. And now, if you look at the connections between major corporations or any company, if you look at the vast majority of those connections, you're going to find that it's companies that own their own equipment that are using the internet as that giant backbone, but still providing secure communications. No longer can AT&T dictate what those connections are. When we started the company, it was like the first or second year, 1997, 1998. I had a company up in, their headquarters was in South Bend, but their main business was in Buchanan, Michigan. Okay? Buchanan, Michigan. They needed to connect, it was called FurnitureFind.com, which I don't even know if that domain even exists anymore. FurnitureFind.com. What do you think that was for? FurnitureFind.com. I mean, that's an obvious.
Use furniture.
Cole?
Couches and chairs
You buy your furniture online. Completely new concept. Revolutionary concept. First one in the country. These people came up, FurnitureFind.com. They had the site earlier, but it wasn't really that efficient. So what we did was, we connected their Buchanan, Michigan connection, or the Buchanan, Michigan data center to the internet, and then allowed their outlying stores to connect to that also. We used VPN technology and internet connections. However, at that time, we had to contract with AT&T first to get the physical connection that was robust enough to handle the volume. And then we had to connect to a company that was one of the only internet service providers that was big enough to handle it, called PSI. Okay? We had a 100 megabit connection, which some of you may even have that in your business or in your homes now. 100 megabit connection. It cost that company $32,000 a year, a month, to maintain that 100 megabit connection. $32,000 a month to maintain that. 100 meg connection now, I've got a company up in South Bend, actually no, here in Plymouth, that has a gig connection up to the link. They have a 100 meg connection to the internet. So in other words, a gigabit connection backbone, that's just the data backbone, to South Bend, and then a guaranteed 100 megabit connection for internet access. They're paying less than $1,000 a month. And that's both ways, 100 meg up and down. That's how much it's changed in what I consider a very relatively short time. So that's X.25. The X.25 packet, you don't have to memorize all the components of this. You just have to understand that at the top, kind of hard to see, but this is in your slides in the book. At the top, you've got the packet header, then you have data, then you have the trailer. Now the trailer is not necessarily the destination. At the top, you've got the destination IP address and the source IP address. In the middle, you've got the actual however much data you have in that particular packet. But at the bottom, you have something that's additional in an X.25 packet. It's data that ensures that the packet gets, or the packet is, the CRC, in fact, it's called cyclic redundancy check, to make sure that that packet is complete and not corrupted. What?
So that's what replaced the overhead, right?
Actually, the overhead is all of those other than the data. As an example, no, overhead is overhead is overhead. No matter whether it's an X.25 packet, frame relay packet, Ethernet packet, overhead is overhead. That's the information that's in, and this is one of the questions, what is overhead? Overhead is that additional information that the information in a packet that is included above and beyond just the data itself. So it would be encryption, it would be destination address, it would be the source address, it would be the CRC, which makes sure that guarantees the destination of that packet has been sent and not abused. All of those kind of things. End flag, it tells you how many bits are actually in the packet itself. It tells you when you're done with that. Okay? Okay, PSE, or Packet Switching Exchange. In general, this has not changed. The general term of packet switching exchange still exists today. Just the technology that it's using for creating those packets and managing those packets is different. So a PSE, consider this, is located at, when they say the central offices, we're talking about at AT&T, at GTE, at CenturyLink, at wherever it is. Okay. When some businesses continue to have leased lines, this is important. Some businesses continue to lease lines from the carrier. Okay? What do I mean by that? Local exchange carrier. Give me an example of a local exchange carrier. Jessica. Like who? I can't hear you. Verizon. There's an example of a local exchange carrier. Sprint or CenturyLink. Sprint in Fort Wayne, CenturyLink here. Four-way. All those are considered local exchange carriers. So you contract with them for the actual lease line. And this could be anything from a 64K connection, which is kind of scary, 64K connection, up to, at least in XDOT 25, up to 3 megabit connection. Okay? 64K chunks. All right, now, this is the part that starts to get confusing. Everybody stop taking notes. I want you to think about this. Just picture this. Let's say CenturyLink. Everybody's got or knows about CenturyLink here. CenturyLink has thousands and thousands of circuits, right? A circuit is from one point to another point. And those circuits may go from Plymouth to Warsaw. There may be maybe 1,000 connections just from Plymouth to Warsaw. There may be 500 connections from Plymouth to South Bend or to Fort Wayne or to wherever we're going. Within those 1,000 connections, you could have virtual circuits that like VPN, but not exactly. If Austin has a company in Knox, Indiana, that he wants to connect to Plymouth, he's going to contract with CenturyLink for, let's say, 1 megabit virtual circuit. Okay? A 1 megabit virtual circuit. That doesn't mean that when he's not using that Jordan's company, which is also in Knox, and actually his is in North Judson and Plymouth, is not using those same physical connections. But he's contracted, Jordan is contracted with Sprint or with CenturyLink to use a 2 megabit connection. So Austin is using the same physical cable that Jordan is using between here and there, but he's only contracted with CenturyLink for a 1 megabit connection. Jordan is contracted with CenturyLink for a 2 megabit connection. Those are virtual circuits using the same infrastructure. That's what originally what made those major carriers cheaper than trying to run your own cable. Okay? Now, the other thing we mentioned, the second bullet, chances of the entire message of packets taking one circuit are slim. The circuits, the virtual circuits, there may be 5 different connections there. I still have a physical circuit that's established, but when Jordan is sending information to the other office in Plymouth, it may take, part of it may take one path, part of it may take another path. That's packet switching, right? He's still guaranteed a 1 megabit virtual circuit, even though the packets may take 15 different paths to get there. But he's guaranteed 1 megabit overall virtual circuit. So because multiple circuits are being used, and somebody describe a circuit. Before we talk about IT, what's a circuit? You all have taken science in 8th grade or 7th grade. Describe to me what an electrical circuit is. Someone besides the ones that always answer the questions. Ethan, what's a circuit? Okay, give me an example. Show me where a circuit is established. Did you ever create a circuit in science class?
Yeah.
Okay. What did you have to do?
We created.
You had electricity.
Yeah, we had to connect it with the battery for one wire for the power on the board.
Yep.
All the way around.
How did what did you have to do to power the light bulb?
Use positive and negative charges to get the battery valve to recharge the bulb.
Okay. How did you control that light bulb off or on? What did you, when you turned the light bulb on, what did you do to the circuit? There's another name for connecting the charge. You probably had a switch, right?
Yeah.
What did that switch do? You're almost there. Somebody help Ethan. What did the switch do? Yes. It opened the circuit. Okay, when you turn on the switch or turn on the switch, like at the light there, it opens the circuit. And as long as that switch is open, that circuit is constantly sending traffic, sending data in the IT world, or sending electricity in the electrical world to that destination. When you close the circuit, it's abruptly changed. It's no longer open. is a closed circuit, so it can't transmit. That's the same way the IT world works. When the local exchange carrier opens a circuit specific to Austin's company, he will always have that connection. There will be multiple circuits making up the flow of data, 5 different, let's say, as an example, 5 different paths or 5 different circuits that are opened up, but they all form one as far as Austin is concerned. That's what that CSU DSU does. It combines all of those. It brings them all back together. Okay? We've talked about hops. This is not just an ingredient in an alcoholic beverage. Okay? Hops, think of these as routers. Reassembles the packets and the overhead header and trailer is discarded. Now, that can be confusing when you read it in your book. If I've got, if Jessica is the source, Zach is the destination, and Jason is the router, he's the hop, right? Why is the packet assembled and disassembled? First of all, what's the IP address between, hold out your right arm. What's the IP address of that interface? What is it? 192.168.0.